This video is going to compare the energy, current, and power in parallel circuits. So here's my little parallel circuit. I've got equal resistances on the top and bottom, and you have to have some prior knowledge. Remember that power is proportional to the current times the voltage, and that the potential energy is proportional to the current times the resistance. That's Ohm's law. As charges move through the circuit, that's going to measure the current, and because they're both 10 ohms on the top and bottom, they'll have the same current in this case, only because the resistances match. But what if they're different? So to understand what's going on, I'll have two different resistances. I'll have 5 ohms at the top, 10 ohms at the bottom. And there are a couple rules and concepts about parallel circuits. One of the things is how they're defined as parallel. Parallel circuits drop the same potential. In other words, they have the same potential difference across them. So that's for the parallel circuit. So the change in energy for the 5 ohm resistor, it's the same drop in voltage. And on the bottom, it's the same drop in voltage as the bottom, I should say. So the top and bottom have the same because they're in parallel. So they're going to use up the same amount of energy. So if I'm comparing the energy of these two in parallel, it's going to be the same. Okay, so let's move on. If I look at the circuit, I've got some kind of current coming into it, call it I naught, going into the junction, and it's going to split into a 5 ohm and 10 ohm part. Now the 5 ohms has less resistance, so for the 5 ohm, I would expect it to have a higher current because the charges are going to move faster through the 5 ohms since there's less resistance. So the 5 ohm has a higher current, and the 10 ohm is going to have a lower current. That's what I'm going to expect. Now I need some way of comparing the currents. What I'm going to do is compare them with the original current. So I'm going to set up a little ratio. The current of the 5 ohm resistor is equal to, well, current and resistance are inversely related to each other. And I'm going to use the other resistor to figure out how much current is going through the 5 ohm because the way the current splits in the circuit. So I'm going to have 10 ohms, that's the opposite resistor, divided by the sum of the two resistances, that's the 5 and the 10. So 10 divided by 15 is 2/3. So 2/3 of the original current, whatever number that is going through the top. And if I do the same kind of math for the bottom, I can take the 5 ohm divided by the 5 and the 10, and I can see that 1/3 is going through the bottom. And that makes sense because 2/3 plus 1/3 equals whatever the original current is of 1 times that. So it adds up the way it should split, and that makes sense. So that's great. I can also see one more thing about this when I'm comparing it, because 2/3 divided by 1/3 is 2. 2/3 divided by 1/3 is 2. So that means I have twice as much current going through the 5 ohm resistor when compared to the 10 ohm resistor. And that makes sense. I've got half the resistance. Since they're inversely proportional, I would expect it to have twice the current. So another way to compare it. Now let's look at the power. Power in the 5 ohm resistor is proportional to the current in the 5 ohm times the potential difference across the 5 ohm. And the power in the 10 ohm is proportional to the current in the 10 times the potential difference in the 10. Well, I know from our earlier statement for the definition of parallel that my energy is going to be the same in each one of these. So the potential difference is going to divide out. That means that my power in the 5 ohm is proportional to 2/3 of the current. So I 5 ohms, I replaced it with my 2/3 I naught. And I'm going to do the same thing for the 10 ohm, replace that with my 1/3 I naught. Now the I naught is going to divide out, so that's great. But I'll get to that in a minute, sorry. So I'm going to take it back a step and talk about where the 2/3 came from and where the 1/3 came from. So that's the 10 ohms divided by 15 ohms. And the bottom one's going to be the 5 ohms divided by 15 ohms. But now the I naughts divide out, so I'll divide them out here. I could have done it above, but I'll do this. And also something else divides out, that's the denominator of my fractions. So the 15 goes away as well. So now the ratio, the power in the 5 to the power of the 10 is equal to 10 over 5 ohms. So if I solve this for the 5 ohms, 5 ohms is proportional to 10 over 5 times the power on the 10, or in other words, the 5 ohm resistor is proportional to twice the power in the 10. So if I'm looking at all this, and I got to do this comparisons, the energies are the same because the voltage drop is the same, voltage proportional to energy. The currents, I know the top one is 2/3 because of the way the current flows to the lower resistance, so that's going to be 2/3. The bottom one is 1/3. I also know the top one is twice the current as the bottom one because it's half the resistance, and they're inversely proportional on a parallel circuit. In terms of the power, I know that the power in the bottom one is twice the power of the bottom one. The power in the 5 ohm is twice the power in the 10 ohm. What that means is if these were light bulbs, the 5 ohm would be brighter, be twice as bright as the 10 ohm resistor.